Chapter 10 in your textbook is on gases. In this chapter, we're going to talk about the nature of gases, the characteristics of gases, and the behavior of gases. All matter exists in the three phases: the solid, the liquid, and the gas. Gases are the most recent of the three to be discovered in great detail because gases were so hard historically to isolate. Substances that are liquids or solids under ordinary conditions can also exist in the gas phase with enough thermal energy. When we find these substances in the gas phase, we typically refer to them as vapors. Oxygen in the gas phase we think of as simply oxygen, but water, which we typically think of in the liquid phase, its gas phase we call water vapor. Gases tend to have properties that differ from those of solids and liquids. For example, gases tend to expand to fill their containers. Gases are also highly compressible. They tend to be poor conductors of heat, and they have extremely low densities. And in mixtures, gases tend to form a homogeneous mixture, meaning that they will mix in all proportions to provide one unique phase. Here we see a sample of common gases. Carbon monoxide, for example, is a colorless, odorless gas. Carbon dioxide, similarly, a colorless, odorless gas. Ammonia is a colorless gas that has quite the pungent odor. Methane gas is colorless, odorless, and flammable. Methane, otherwise known as natural gas. Now, we may not think of it as being odorless, but it turns out that the natural gas that we experience in our homes has a little bit of a sulfur-containing compound in it, which gives it a fairly aromatic odor. Some of the quantities, some of the properties that describe or define the state of a gas are known as variables of state. Common variables of state are temperature, pressure, volume, and amount of substance, typically expressed in moles. Now, we've talked about temperature, we've talked about volume, and we've talked about amount of substance in a fair amount of detail. So we're going to focus our efforts on pressure. Pressure is the mathematical relationship between force and area. It's the amount of force applied to a given area. So if you think about your weight as being force, the force that is being exerted on the earth by you. If you stand flat-footed on both feet, then there's a certain pressure that you are exerting on the earth. If you instead stand on one single tippy toe, you are decreasing the area of contact between you and the earth. The relationship between pressure and area is inversely proportional, as you can see. So as the area decreases, the pressure increases. If you stand on your tippy toes, then trust me, you will feel the pressure or the increased force to area ratio. Atmospheric pressure is the weight of air per unit area. And we see here on the slide an image that speaks to the atmospheric pressure at Earth's surface. Now, if pressure is something that can be measured, then surely it is something that can be quantified. A wise man once said that numbers without units are meaningless in measurement. And for those of you who did not take my 1142 class, that wise man was me. The units of pressure correspond to those units of force and area in the International System of Measurement. The standard unit of force is the Newton. The standard unit of area is the square meter. So 1 Newton per square meter, the amount of pressure that is being exerted by 1 Newton's worth of force applied over 1 square meter's worth of area is known as a Pascal. Now the unit of a Pascal is a very, very small unit. Typically, when we speak of gas pressures, the Pascal is oftentimes scaled up to the kilopascal, where the prefix kilo means 1,000. Atmospheric pressure at sea level is approximately 100 kilopascals. You'll see on this slide that that also refers to a bar, yet another unit of pressure. Whenever we look at storm data, perhaps hurricane or tornado data, when they talk about things like wind speed and the pressure inside the storm, perhaps we've heard them refer to 973 millibar worth of pressure, a lessened pressure, a low pressure situation inside a storm. In addition to the Pascal, in addition to the bar, we have millimeters of mercury. Now, I know that that seems a bit awkward. Millimeters of mercury as a unit of pressure. Millimeters seems to be a unit of length. Well, when applying this unit of pressure, we need to imagine a barometer. A barometer, which is a device used to measure pressure. If you look on the right-hand side of the slide, you will see what appears to be a reservoir of mercury. Immersed in that mercury, there is a glass tube that has been evacuated, which means there's no air, there's simply vacuum. If we immerse the tube in the mercury, then the pressure that the air exerts is going to push the mercury down, and it is going to go up inside the tube. Since there's no air in the tube, there's simply vacuum. How high does it go up in the tube? Well, that depends on the amount of pressure being exerted by the air. If 760 millimeters of mercury is the height of the mercury in the column, that means that the air will exert enough pressure to support a column of mercury that is 760 millimeters high. In order to avoid confusion, the unit millimeters of mercury has been named the torr. Another unit of pressure is the atmosphere, where 1 atmosphere is equal to 760 torr, or 760 millimeters of mercury. Standard pressure, or more appropriately standard atmospheric pressure, is the normal atmospheric pressure at sea level. It's essentially equal to 1 atmosphere, which as a conversion is equal to 760 torr, which is equal to 101.325 kilopascal, which is equal to 1.01325 bar, which is also equal to 14.7 psi, or pounds per square inch. If we revisit the equation for pressure, force per unit area, we think of force in terms of pounds, perhaps, and area in terms of square inches. So 14.7 pounds per square inch. While it does not represent the SI units of pressure, it does follow the scheme of force per unit area. The pressure of a gas essentially results from the collisions within the walls of its container. The magnitude of the pressure is determined by how often and how hard the molecules strike the wall of the container. Now, since we've now discussed pressure, and we know volume, temperature, and amount of substance are all variables of state, we need to come up with a description of how a gas exists. With those four things in mind, what happens if we take a sample of gas and we increase the temperature? What happens to those other variables? Well, with any scientific endeavor, if we're going to change one variable, we need to hold everything else constant in order to make sure that the result that we see is based on the change that we made. Take the following example into consideration. If I ask you to take a test on day one, and you take that test, and then I come back the very next day and say, I want you to take the same test, except during that test I play some really loud music and I flick the lights on and off, on and off, on and off. And then I walk by intermittently and take your pencil out of your hand and put it back. Take your pencil out of your hand and put it back. If you don't do well on that exam, why didn't you? Was it because of the lights? Was it because of the sound? Was it because of the annoying professor who was removing the pencil from your hand on a regular basis? We have to isolate what the problem is, or what the variable is, in order to determine exactly what the cause of the change was. So scientists much smarter than I decided that they were going to isolate the variables, change one variable, and see what the effect would be on another while keeping everything else constant. The first one that we will discuss was the work of Robert Boyle, who decided to investigate the relationship of pressure to volume. So while taking a sample of gas, a fixed amount of gas, which means that we did not increase or decrease the number of moles of gas, if we hold that gas at a constant temperature, what is the relationship between pressure and volume? If we increase the volume, what happens to the pressure? Well, imagine if we increase the volume of a container in which a gas is confined. If the same force is being exerted, by increasing the volume, you're giving the gas a larger area over which to interact. So with a larger area, that means that the pressure would go down. Remember, the relationship between pressure and area is inversely proportional. So as the volume goes up, the pressure goes down. We don't see that force to area ratio increase. Mathematically speaking, we see that as one goes up, the other goes down. So the product of pressure and volume turns out to be a constant value. If one increases, the other decreases. If we compare two conditions, a sample of gas before and after a change takes place, that means that P1 times V1 is equal to P2 times V2. If the pressure doubles, it is a result of the volume being cut in half. If we look graphically at this information, then we will see that a graph of pressure and volume will not be linear, but the inverse of pressure versus volume will indeed be linear. So there's an inverse proportionality between pressure and volume, and we'll keep that in mind as we look at other relationships. Jacques Charles investigated the relationship between the volume of a gas and its temperature. If we take a fixed amount of gas and we hold it at a constant pressure, that means that the force to area ratio remains constant. then we see a direct proportionality between the volume and its temperature. In other words, as we see an increase in temperature, we're going to see a subsequent increase in volume. As we see an increase in volume, we would see a subsequent increase in temperature. If we expand a gas into a larger volume, in order for that pressure to remain the same, the molecules themselves have to speed up or apply more force per unit area. So we see that as the temperature increases, so does the volume. Heat up a sample of gas. When we heat something up, it tends to expand. When we cool something down, it tends to contract. In other words, take up less space. The relationship holds true that an increase in volume represents an increase in temperature. So mathematically speaking, the ratio of V to T gives us a constant. This means that if we take a sample of gas and it undergoes a change, that the V over T ratio is going to be constant. V1 over T1 is equal to V2 over T2. Now, the important thing to take note of is that the temperature must be in Kelvin. What this relationship suggests that if we double the temperature, we're going to see a doubling of the volume. So what is -2 degrees Celsius doubled? Is it -4 degrees Celsius? Obviously not. -4 degrees Celsius is a colder temperature than -2 degrees Celsius. So we're going to operate in a temperature scale that doesn't have negative values. Okay. If you look at the image to the right of this slide, you will see the behavior of a gas when cooled to its lowest temperature. That lowest temperature we find -273 degrees Celsius or 0 Kelvin, otherwise known as absolute zero. Guillaume Amonton gave us the relationship between pressure and temperature when holding the volume constant for a fixed amount of gas. So let's imagine that we have a container of a fixed volume. It's not going to increase or decrease in volume. If we have a certain amount of gas in there and we increase the temperature, in other words, we make the molecules move faster, then they're going to collide more often with the walls of the container, which means that they're going to exert more force over that same area, giving us a larger pressure. So an increase in temperature is going to result in an increase in pressure. If you think about your tires, if we assume that your tires are a constant volume situation, and as you drive, the road heats up the gas in your tires, which means that they will apply a greater pressure. If you simply look at a seasonal situation, your tire pressure in the winter, when the temperatures are colder, is going to vary from your tire pressure in the summer when the temperature tends to be warmer. Once again, it should be noted that the units of temperature must be in Kelvin for this relationship to hold true. Avogadro's law, named after Amadeo Avogadro, he of 6.022 times 10 to the 23rd fame, suggests that the relationship between the volume of a gas and the number of moles of gas is directly proportional when holding the temperature and the pressure constant. So let's take, for example, a gas under a specific set of temperature and pressure conditions. Let's say 1 atmospheric pressure and a temperature of 0 degrees Celsius or 273 Kelvin. The number of moles of gas being directly proportional to the volume suggests that the identity of the gas doesn't matter. If you look in the upper right-hand corner of this slide, you will see 3 samples of gas at 0 degrees Celsius and 1 atmosphere of pressure. It turns out that 1 mole of gas, regardless of the identity of the gas, under these conditions is going to occupy 22.4 liters worth of space. Now, those conditions, 0 degrees Celsius and 1 atmosphere, refer to standard temperature and pressure. And so it doesn't matter if it's helium, it doesn't matter if it's hydrogen, it doesn't matter if it's sulfur hexafluoride. Any gas will occupy 22.4 liters worth of space per 1 mole of gas. So the mathematical relationship given by Avogadro's law is that the molar volume remains constant, V over N, which technically is the inverse of molar volume, remains constant. For more moles of gas, under those conditions, we're going to see an increase in the volume. So we combine these relationships in order to see how the variables of state work together to describe the behavior and the nature of a gas. Boyle's law, which shows an inverse proportionality between pressure and volume. Charles's law and Avogadro's law, which show direct proportionalities between the volume of a gas and the temperature and the number of moles of gas. Even Amonton's law, where we see the relationship between pressure and temperature, which is indeed a direct proportionality. When we combine these laws together, then we get a relationship of volume to temperature, of volume to number of moles of gas, and of volume to pressure. Now, this does not represent an equation. This is simply a proportionality. We can turn that proportionality into an equation by introducing a proportionality constant. And when we do so, we establish what we call the ideal gas equation. So the relationship of pressure, volume, amount of substance, and temperature, those 4 variables of state, combine to give us a proportionality constant known as R, or the ideal gas constant. For a gas that is behaving ideally, we see the relationship of PV over NT equaling a constant value. That R value can have many units, and those units are dependent upon the units of pressure, volume, amount of substance, and temperature. At the bottom of the slide, you can see a series of values of R. And the one that we choose to use is very much dependent upon either the information that we want to know or the information that we have. For example, if I know the pressure that a gas exerts, if I know how many moles of gas I have, and I know the temperature of the gas, I can determine the amount of space that that sample of gas occupies, or its volume. If I know the temperature of a gas and I know the volume of the gas and the amount of pressure that it exerts, I can tell you how many moles of gas there are in that sample of gas. As with any equation, the things that you know can be used to find the things that you want to know. So we can use the ideal gas equation to figure out some fundamental quantities of a gas. For example, the density of a gas can be determined by rearranging PV equals nRT, with the understanding that the number of moles of gas is related to the mass of the gas by the molar or the molecular mass. Rearranging PV equals nRT results in the density, which is the ratio of the mass to the volume, being equal to the molecular mass or the molar mass of a gas times the pressure that that gas exerts divided by RT. And once again, the units are very important. We can also use information from the ideal gas equation in order to determine the molar mass of a gas. For example, if we have a sample of unknown gas, of unknown identity, then we can determine the molar mass of the gas, which is a step in determining its identity. If we know the mass, the volume, the temperature of the gas, and the pressure that it exerts, then we can find its molar mass. If the ideal gas equation holds true for a gas at any instant, then we can account for any changes that take place in any of those four quantities. Think about a sample of gas under a certain set of conditions. Now, what happens to those conditions if we change one or more of the variables? What happens to a sample of gas if we increase the temperature as well as decreasing the volume? What happens to the pressure of that gas? Well, if the gas is behaving ideally, then we can account for all of these changes through what's called the combined gas law. Imagine that PV is equal to nRT under a certain set of conditions. That means that at a later date, PV is still going to equal nRT. That's the point of that proportionality constant. If we change two variables, we can see how the third will be affected for a fixed amount of gas. If we keep a sample of gas fixed, then obviously the value of R is not going to change. It's indeed a constant. Then PV over T is going to be a ratio that holds true forever and ever and a day. Now, the foundations of the ideal gas law lie in the kinetic molecular theory, or the kinetic model of gases. This particular theory suggests that gases consist of large numbers of molecules that are in ceaseless or constant random motion. It also suggests that the combined volume of all the molecules of a gas is negligible, really small, relative to the total volume in which the gas is contained. Another way of saying this is that the size of the gas molecules is significantly smaller than the distance traveled between collisions of gas molecules. Another tenet or basic assumption of the kinetic molecular theory is that gas molecules only interact during collisions, that there are no attractive or repulsive forces between gas molecules. Energy can be transferred between molecules during those collisions, and those collisions are elastic, which suggests that the average kinetic energy does not change over time. And finally, the average kinetic energy is proportional to the absolute temperature. And for the most part, these are reasonable assumptions to make when putting forth a simplistic model of gas behavior. We don't model things in a complex manner and get simple. We start with the simple and then we add in other factors when things get difficult. Things are about to get difficult. The assumptions at the heart of the kinetic molecular theory tend to break down when a gas exerts a high pressure or exists at a low temperature. The idea is that these gas molecules do not interact with one another except during collisions. Well, we know that to be untrue. If you are to slow down the motion of the molecules, you can get a better sense of the attractive and repulsive forces that do exist between gas molecules. As it stands, gas molecules have a great degree of kinetic energy. That means that they're moving really, really fast. So as two gas molecules travel by one another, then maybe they don't have time to interact. The protons associated with one molecule and the electrons associated with another molecule may not have the time that it takes in order to see an attraction formed. The repulsion of one molecule's electrons with another molecule's electrons may not take effect if the molecules are moving fast enough. But when you slow down the motion, then perhaps we can find interactions and repulsions which go against the kinetic molecular theory. At high pressure, we see a similar deviation from ideal behavior. If you confine a gas to a smaller volume, Boyle's law suggests that we're going to see an increased pressure. A smaller volume means that these particles are going to be forced to interact with one another. So the assumptions that suggest that molecules do not interact with one another, they're just not true. The assumption that the molecules of a gas have an infinite volume, it's just not true. Molecules do interact, whether they be attractive forces or repulsive forces. And molecules do have a finite volume. But it's nice to imagine a world in which this behavior, this simplistic description of gases is indeed true. We don't have to deal with the repulsive and attractive forces of a gas. Now, in order to fully discuss this, we would have to introduce things like the virial equation of state and the van der Waals equation of state. These things I'm going to hold off on discussing until Chemistry 3381, which is Physical Chemistry 1. I look forward to speaking to all of you in a year or so. Well, this wraps up our discussion of gases. When next you hear my voice, it will be in a discussion of liquids and intermolecular forces. Good day, good evening, and good night.